Okay, so hello everyone, welcome to another asynchronous lecture of thermal physics. And this is really following up from the previous lecture on classical statistical mechanics and like Boltzmann's entropy. This is about what to do when you apply classical statistical mechanics to systems which are really made of quantum identical and indistinguishable particles. Okay, so there is a very subtle important difference between identical particles, which happens when you have a gas of non-interacting molecules which are all the same. You have a single component system, all your molecules are identical to one another, and classically speaking you assume that although they look the same, you can always tell which particle is which. So if at any given instant of time you give them labels, then you could in principle track down the trajectories of each individual particle, and at any other later instant of time you could freeze the system and you could tell where did every single one of the particles that you labeled go to. Okay, so this is a very classical picture to have in mind. The reality of it is that when you have bunch of identical quantum particles that are indistinguishable from one another, they will exist in a collective state, and as time goes by this collective state will change, but you are not going to be able to tell this particle was here at this time and then it's in the other place at the later time. You just know about their collective state, not about their individual trajectories. And just to reflect this into the formalism of classical statistical mechanics, we have to change the way we count the number of microstates which are compatible with any given macrostate. Okay, and so that's the only thing we do in this lecture. So first thing is we are going to define our macrostates differently. So before, what we did was to count how many particles were in each of the possible single particle states of our system. And now we are going to even forget a little bit more information in general, and we are only going to count how many particles have a certain single particle energy value. Okay, and actually there could be several different phase space cells or individual states of the system that have the same energy. Okay, but we are going to lose track of which state is which, and we are only going to count how many particles have a certain energy. And then this will introduce the concept of energy degeneracy. And when we think about identical particles which are classical and distinguishable in the classical sense, we are going to recover Maxwell-Boltzmann statistics that we already derived in the previous lecture, but with a little correction to take into account the degeneracy. Okay, we just multiply essentially by the degeneracy. And when we have properly indistinguishable particles, I'm going to explain in an example what it means for particles to be indistinguishable when you try to count the compatible microstates. And we're going to see what happens in general with the Bose-Einstein statistics. That is, I have identical particles which are indistinguishable, but there's no other rules that apply to how these particles can combine in any given state. But if we impose that these particles have to obey Pauli exclusion principle, so they cannot coexist, two particles or more, in the same state, then we're going to get completely different statistics, and this is the Fermi-Dirac statistics. And we are going to see how, by taking the low density limit, that's kind of a classical limit of either the Bose-Einstein statistics or the Fermi-Dirac statistics, we recover the Maxwell-Boltzmann distribution. Okay, well, like statistics, not distribution in the sense of velocities, which is a different thing. So that's essentially what we're going to do. And we're not going to elaborate what we can do with this Bose-Einstein or Fermi-Dirac statistics, but in the next self-study pack of the module, which is not assessed and it's optional, you are going to see applications of the Bose-Einstein statistics to the problem of blackbody radiation, and the Fermi-Dirac statistics to the modeling of a metal. Okay, and these things are things you actually have seen already in condensed matter physics, but it's also nice to see them here in thermal physics, appearing slightly differently perhaps. So okay, that's a summary for the lecture, and we're going straight away with the first video.